Welcome to the Algebra 2 Chapter 10 review. Here we'll go through all the problems on the review guide and really just pay close attention on how the language of the problem dictates what method we're going to use to set up and solve these probability and counting principle questions. There's a lot happening in the language, and then usually after that it's a quick calculator entry to get our answers. So we just want to make sure we're typing in the correct things. All right, so let's get started. Problem number one, here we got a two-way table showing different levels of high school students and then what type of cell phone they have. So letter A says find the joint relative frequency for a sophomore owning a Samsung phone. Well, joint relative frequency, joint frequency just means anything that's not in the totals, the margins, and if it's relative, it means it's over our grand total. So here we're looking for sophomores that own a Samsung phone. There are 19 of them out of the 290 total. So there's our joint relative frequency, and you could also have a decimal for that, but I think the fraction's a little bit better. Definitely less time if we don't bother to type that into a calculator. Obviously, if we are leaving our answers in fraction form, we should simplify if we can. In this case, we cannot. Letter B, what is the marginal relative frequency that a respondent owns an Apple phone? Okay, well, marginal, that means we're in our totals, and it is still relative, so it is still over the total. Let's look at our Apple phones. That's 126 out of our 290 total people surveyed. And we can simplify that fraction down to 63 over 145. And again, decimals are totally fine, so if you choose to answer that way, not a problem if you don't want to worry about simplifying those fractions. I only ask that if you are leaving answers in decimal form, please round them to 4 decimal places. That way we get an accurate reading on the actual frequency there. And letter C, what is the probability that if a student is chosen at random, it's a sophomore with a phone that's neither Apple nor Samsung? Okay, well, our sophomores that have the other type of phone, there's only 4 of them, so we have 4 out of that 290 total, and that simplifies to 2 over 145 for that probability. Next, here we have to construct our own two-way table. A recent survey of high school students and teachers found the following results to a survey question that asked, should students be encouraged to use laptops to take notes in class? There were 500 people surveyed in total. Of the 408 students surveyed, 295 answered yes to the question. 52 of the 165 people who responded no were teachers. Organize this information into a two-way table to answer the following questions. All right, so one of the big things that we want to set up is how do we label these? And we've got 2 major distinctions. One is that we've got students and we've got teachers. Now, I'm setting those up as my rows. You could also have those as columns and just kind of flip-flop this table. The same numbers would go in the same places, so we would be able to get the same results. How you see fit is really up to you. The other distinguishing factor is how they responded. So we got yes and no. Okay, and then our margins, well, we're just going to calculate the totals of each row and column. Okay, so we had 512 people surveyed in total. That's our grand total. Okay, 408 students surveyed. 295 students answered yes. Okay, 165 people responded no. That's a total. 52 of those were teachers. All right, so there's the information that was just provided in the question. We're just going to have to use some simple subtraction to find the remaining values. So our total number of teachers had to be 104 to get that 512 total. Likewise, the total number of yes votes had to be 347 to make that row total up to 512. And we find that 113 students voted no, smart kids, and 52 teachers voted no, or sorry, 52 teachers voted yes. 52 also voted no, I guess. All right, letter A says, what's the probability that a randomly selected person that responded no is a student? So we're only selecting a person that responded no. Okay, that means we're only choosing out of 165, only out of the people that answered no. What's the probability that that is a student? Well, the students that answered no, there was 113 of them. So 113 over 165, and that does not simplify, so we can leave that as our answer or have a decimal equivalent. Again, rounded to 4 places for accuracy. Letter B, what is the probability that a randomly selected person from the survey, so this is out of anybody that took the survey, is a teacher that responded yes? Okay, so our teachers that responded yes, there were 52 of them out of the entire number of people that took the survey, 512. And this fraction does simplify all the way down to 13 over 128. And again, we could have a decimal equivalent if we wanted. Of the entire test, I would say that the two-way tables maybe take the most time. The other ones are pretty quick with a calculator, but these, we have to kind of make sure everything fits into place. So just be sure we're taking care when we do that. All right. You order a new computer keyboard from Amazon only to find that all of the 26 lettered keys have fallen off during shipping, and they're loose in the bottom of the box. If you randomly draw one key out, what's the probability that it is Q, W, E, R, T, or Y? So the probability of that event, well, if it's one of those desired outcomes, there are 6 possibilities there for letters out of the 26 total letters that we had in the box that had fallen off the keyboard. That simplifies down to 3 over 13. Or we could have a decimal equivalent. Number 4, when we played Pass the Pigs in class, we found the probability of rolling a trotter with one pig was 2 out of 25, while the probability of rolling a snouter was 3 out of 98. You roll a pig 2 times. What is the probability that you roll a snouter and a trotter? Okay, well, here's an and, so we've got independent events. So rolling a snouter is 3 98ths, and times rolling a trotter is then 2 25ths. And that fraction does simplify. It's 3 over 1225, or a decimal equivalent, 0.0024. But again, I'm just going to stick to the fractions for this review. Just realize that you could have answered with a decimal or a percentage. That's another way of writing probability. Okay, number 5. In an item box in Mario Kart, there are 4 green shells, 2 bunches of bananas, 5 mushrooms, and 1 blue shell. If you were to draw 2 items out of the box, one at a time, without replacement, what's the probability of choosing a mushroom and a blue shell? Okay, this without replacement thing is pretty key. That tells us we have dependent events. So our sample space is going to change. Okay, well, of all the items, I've got 4 plus 2 plus 5 plus 1. That's 12 items total in the box. There are 5 mushrooms out of the 12 for my first event, and if I draw that mushroom, now there are only 11 items left in the box. That sample space has changed. Then, getting the blue shell, there were only one of those in the box to begin with, so there's 1 out of 11 when I make that second draw. And if we multiply those together, we get 5 over 132 for that probability. Moving on, number 6, events A and B are independent. Find the missing probability. Well, independent, that means we're multiplying together, right? And you can see it says probability of A and B. Okay, but we got to find one of the pieces along the way. Okay, so we're multiplying those together. That means that 0.74 times, I'm just going to use an X so I don't mix up my decimal points there, whatever the probability of B ends up equaling, that is going to make 0.63. And I'll just divide away the 0.74 from each side, and I find that the probability of B has to be 0.8514. And I should call that 0.8514. I mean, we should know that probability has to be between 0 and 1, so we should know where the decimal point goes. But sometimes that 0 out front helps us find the decimal point. All right, for the next one, you're drawing 2 cards from a standard 52-card deck, one at a time, with replacement. Okay, so now we're putting that card back after we make the first draw. What's the probability you draw an even numbered card and a face card? Well, let's think about our evens. For our evens, the way we could get that, that outcome to occur, I could draw a 2, a 4, a 6, an 8, or a 10. Okay, the face cards Jack, Queen, and King, well, J, Q, and K are not even, or they're not even numbers, so they're not included in this set. But I've got those 5 cards times the 4 suits, because really there's 4 2s in the deck, 4 4s, 4 6s, 4 8s, 4 10s. There's 20 even numbered cards total. Okay, then a face card, well, that's Jack, Queen, or King. And again, there's 4 of each of those for representing each of the suits in the deck, 12 face cards total. And we've seen problems like that show up a number of times. All right, so with replacement means my sample space does not change. The first draw, an even numbered card, is 20 out of 52. And the second draw, 12 face cards out of, we replaced it. So it's that full 52 card deck again. Okay, and if we multiply those together and simplify the fraction, I get 15 over 169. And the decimal equivalent is 0.0888. Number 8, you have a drawer that contains all the pens you've accumulated over the years. There are 4 neon pens, 6 blue, 12 black, and 8 glitter pens. You randomly choose a pen out of the drawer. What's the probability that you choose a neon pen or a glitter pen? You're only choosing one pen out of the drawer. It's an OR case, so these are events that are disjoint. We are adding the probabilities together. And the total number of pens we've got, 4 plus 6 plus 12 plus 8, that's 30 pens total in the drawer. That's a lot, but you've accumulated them over some years. Okay, a neon pen, that's 4 of the 30. Or a glitter pen, that's 8 of the 30. And again, since our sample space is out of those 30 pens, the denominators stay the same. We have a common denominator, and we add those fractions together, we get 12 out of 30, which simplifies to 2/5. And it makes sense. 2/5 is pretty close to 1/2, and 4 and 8, that's 12 of our 30 pens. Pretty close to half the pens are neon or glitter. And number 9, you roll a 6-sided die, find the probability of A or B occurring. Event A, you roll an even number. Event B, you roll a number that is less than 3. Well, we've got to be careful because we do have overlapping events here. The result of a 2 is actually counted twice. So an even number, that's 3 out of our 6 possibilities. Or a number less than 3, well, that's just 2 or 1, 2 possibilities out of the 6. But we counted the result of 2. That one possibility out of 6 got counted twice. So I need to subtract away that overlap one time to counteract the fact that it was counted twice. Okay, and if I add up all those fractions, again, they have that nice common denominator. Since it's the same sample space, we get 4/6 or 2/3. Okay, number 10, events A and B are disjoint. That means there is no overlap. And oops, I'm catching a typo here. This one held on the 1 key a little bit too long. It should be 1/12, not 11/12. Okay, so the probability of A or B is going to be 4/9. Since they're disjoint, I'm just adding in the 1/12, and there's no overlap, so there's nothing to subtract away. Okay, if I'm adding these up by hand, I would get a common denominator of 36. That's 16 over 36 plus 3 over 36, giving me a final probability when I sum those up, 19 over 36. Again, we could have a decimal equivalent if we choose. Number 11, a recent study found that 72% of high school students have either a savings account or a checking account. The same study found that 65% of high school students have a savings account, and 34% have a checking account. If a high school student is chosen at random, what's the probability that he or she has both a savings account and a checking account? So this is our overlapping situation again. So we do have overlap to contend with, And actually that overlapping piece is what we're solving for. We're solving for the and. So let's have a look. 72% is our or case. So here I'm just going to show you that formula so we kind of fill that in. The probability of savings or, oops, no, that's an and case, savings or checking is equal to the probability of savings plus probability of having a checking account minus the probability that they have both savings and checking. Okay, so what do we know? We know that the or situation is 0.72, representing that 72%. Okay, the savings account is 0.65 for a probability. The checking account is 0.34, and then that overlapping, the and situation at the end, that they have both types of accounts, that is our unknown. So if we combine like terms and solve, we find that negative 0.27 is negative the probability of that overlapping portion. So our answer is 0.27 or 27%, since that's how the question was phrased. That's a pretty good way to answer, or 27 out of 100. Okay, and 12, 13, and 14, simplifying factorials. For 12 and 13, you will be given the formulas for NCR and NPR. So if we look at these and cannot remember how to set those up, worry not, those formulas will be given. We just need to know how to simplify once we have the numbers plugged in. So for number 12, we've got 14 factorial over 14 minus 7, which is 7 factorial. And to simplify that, all we're going to do is we're going to expand the larger factorial until it matches the smaller one. So 14 times 13 times 12 times 11 times 10 times 9 times 8 times, then it finally matches. We get to 7 and it's going to keep counting down just like the denominator does. So we get our cancellation to occur, then we can turn to the calculator and we get 1,441,440. Okay, and of course, if I were taking the test, I would take the time to use that calculator feature, type in 14P7 using that Math PRB menu, just to make sure that we did our arithmetic correctly. For number 13, here we've got 15C5, that's 15 factorial over 15 minus 5, that's 10 factorial, times the amount we're choosing, that's 5 factorial. Okay, now since there's more than one in our denominator, more than one factorial, we're going to expand the largest until it matches the next largest. That will provide our biggest cancellation. 15 times 14 times 13 times 12 times 11 times, then we finally match that 10 factorial. And in the denominator, I'm just going to switch the order here and expand out that 5 factorial, 5 times 4 times 3 times 2. I don't really need to write times 1 because that's not really doing anything there. And then we have our 10 factorial that we designed, or that we expanded out with the intent of canceling. All right, now at this point you are free to use your calculator, but we can simplify quite a bit along the way. This 4 times 3 is like a 12 in the denominator, and we've got a 12 in the numerator. Okay, 5 and 15 simplifies to 3 over 1, and 2 and 14 cancel to 7 over 1. So we do have some simplifying that occurs, and if we type those in the calculator, the 3 times the 7 times the 13 times the 11, we get 3003 for that answer. And number 14, we've got an expression that's a factorial. It's already written that way, so we just need to simplify it. I'm going to expand out the 11 until it matches the 8 factorial, and just realize that I've still got a 3 factorial in the numerator. But we got that big cancellation to happen. The 8 factorial canceled out, so I've got 11 times 10 times 9 times 3 factorial, which is 3 times 2 times 1. And if we type that into a calculator, we're at that stage of the game, we get 5,940. All right, we're cruising right through this. Number 15, you have 14 songs on a playlist on your iPod. When the iPod shuffles the songs, it takes all those songs and puts them in a new order. It arranges them into a new way, and then it just goes right down that new list to play them. So how many different arrangements of this playlist are possible? Okay, so here we're at the point in the test where we can rely heavily on the calculator. We just need to know when order matters or not so that we type in the correct thing. Here we're finding out how many ways we could arrange all of those 14 songs. So it's arrangement, order matters, 14P14, and we get a huge number. The calculator will actually put it in scientific notation, and that's fine. For an answer, it's a huge number of ways. Here's what my calculator output: 8.71782,912, and then it says e to the 10th, but that means times 10 to the 10th power. Okay? Or if you have a calculator that displays more digits than that, it would write that as a full number. But realize scientific notation is okay when we're talking about these really, really huge numbers. And since I believe most people have calculators set the same way that I do here, I would expect that that's the answer we would receive. Don't you worry, on the test you will not have any answers that show up this way. It's possible when we're finding these number of ways. There are huge numbers of ways for arrangement problems to occur. So don't worry, the calculator will not give you scientific notation on the test. All right, number 16, Chili's is promoting a dinner for two offer where couples can order an appetizer, 2 entrees, and a dessert from a special menu for a discounted price. If there are 5 appetizer options, 8 entree options, and 4 dessert options, how many different dinners are possible? Okay, well, this is our textbook menu problem. Okay, it really is a menu. And we just need to think, okay, how many options do we have for appetizers? And how many options do we have for our entrees? And how many options do we have for our desserts? Now, we want to be careful. It does say that we have 2 entrees. So how many appetizers can we choose? Well, different appetizers, we've got 5 of those. For our entrees, since we are choosing 2 of them with replacement, right? Because we could have 2 couples that order the exact same entree. Okay, we've got 8 to the 2nd power. It's like an 8 times 8 situation there. So you could have split that up into 2 entree blanks if you wanted, or just realize that those 8 options are available to both people. And then lastly, 4 dessert options. So we've got 5 times 8 squared times 4. We get 1,280. All right, and we want to be careful. It may be tempting for this entree section to say like 8 options, choose 2, but that's meaning that the people are choosing different options when they could in fact choose the same one. So we do not want to do 8 choose 2 there, just because those people could choose they both have 8 options to choose from. 8 for the first person and 8 for the second. 17, a company is trying a radical new policy where they take all of their employees and randomly assign them different positions in the company for a day. If there are 37 employees, how many ways could the CEO, the vice president of operations, and the messenger be chosen? Okay, so it's kind of like doing a first, second, and third place finisher. So we do have an order mattering here. There are 37 employees. How many ways could I arrange 3 of them in those 3 different positions? And so we've got a permutation, 37P3, and we find that that's 46,620. Again, be on the lookout for when there's an order that's affecting our result. Number 18, and try and squeeze this in the margins on my PowerPoint slide here. On the 11th day of Christmas, your true love gave to you 11 pipers piping. How many ways could you choose 6 of them to play the bassoon instead? All right, well, It doesn't matter what order we choose those people. We're just choosing 6 of our 11 and having them play a different instrument. So we've got a combination 11C6, and we'll let the calculator do the heavy lifting there. With that one, we get 462. Right, and the final problem of the review. According to a national survey, 47% of Americans believe the moon landing was a hoax. You randomly ask 5 people if they feel the moon landing was a hoax. Draw a histogram of the binomial distribution for this survey and answer the questions below it. Now you can see you do have the formula there for a binomial distribution, and we're going to use that to fill in the table. So just as a reminder, here's how I'm typing this in to get a quick calculation of the table. In my y equals menu, I'm typing in 5, that's the number of trials I have, choosing x of them to be successes, right? How many ways could I arrange those people that do believe it's a hoax? Then I've got times the probability of that success, 0.47, to that number of successes power, times, well, we had so many successes, we also had so many failures. That's 1 minus the 0.47 to the, how many trials remain? 5 minus x power. So that's how I'm typing that into the calculator to use x's as inputs in the calculator instead of k's in our table. All right, so if I type that in and look at the table, these are the decimals that I come up with. Your calculator may round them differently, but I would copy down what the calculator is showing you exactly. We want to be as accurate as possible. So I get 0.04182 for 0 people believing. I get 0.18543 for 1 person, 0.32887 for 2 people believing, 0.29164, 0.12931, and 0.02293 for all 5 people believing that moon landing was a hoax. All right, now in order to tell what's the most likely outcome, well, we can use our table and look for the highest probability in that output, but it would be nice to set up a little distribution there. We're going to be working with graphs of distributions when we get to chapter 11, so it's nice to understand and interpret those. Our input variable is k, and the output is the probability of k successes. So let's mark out all of our options. We got 0, 1, 2, 3, 4, and 5. Okay, and I'm just going to kind of particular about these lines being parallel, so I'm just going to take some time to make some dashed lines here so that my columns actually look nice. They're not bending all over the place, making a Salvador Dali painting, the melting clocks. And then my y-axis, you can see I made 7 tick marks. That's so I can count up by nice little 0.05 increments. And end up at 0.35, which is higher than the highest probability I saw as an output. All right, so we'll fill that in. The first one almost at 0.05. Okay, the next one, 0.18543, almost at 0.2. Next one, 0.32887, almost to the top of our graph. 3, I got 0.29164. For 4, I've got 0.12931. And for 5, 0.02293. All right, so there we have that distribution and can clearly see what's the highest probability. So to answer letter A, what's the most likely outcome? Well, it's that 2 of the 5 people believe that the moon landing was the hoax. All right, and letter B, what's the probability that at most 3 of the 5 people believe the moon landing was a hoax? Well, at most 3 of the 5 means that I got to find the probability that 0 people were believers, or 1 person was a believer, or 2 people were believers, or 3 of them were believers. That means 3 at the most. So I'm going to look at those probabilities in my table and sum those up. And if we total those up in the calculator, I get 0.8478. Okay, it is an OR situation, so just like we talked about with disjoint and overlapping events, that means we're adding probabilities together. All right, so there you have it. That's all we're covering here in Chapter 10. Quite a bit. But again, if we focus on the language, a lot of these problems can be done very quickly, and we should be able to have some idea if these answers make sense. We've seen huge numbers when we're counting and using combinations and permutations. We should know that probabilities should end up being between 0 and 1. And we've got this binomial distribution that we should be able to tell our situation based on this formula, what the outcomes are going to be. So really neat, interesting real-world math in this chapter. I love teaching this chapter. I think it's really neat to see how these different scenarios that are very likely in the real world to kind of calculate how likely they are to occur. So pretty neat. I hope you've enjoyed it, and good luck on the test.